My friends, hello, welcome to this special video. When we talk about air safety, what are we really talking about? We are at the interface between humans and machines at that point where all kinds of errors can happen, and when they accumulate in a certain way, they can lead to a tragedy. Well, this mechanism shows up everywhere. Today, we're going to talk about an industrial accident that claimed the life of an employee of a company belonging to a French group, even though it's based in the United States. And you'll see that in principle, the mechanisms are always the same. Let's start by maybe talking about an accident that happens regularly in kitchens, in everyone's kitchens. In fact, firefighters often demonstrate by taking a pan with oil, vegetable oil. They heat it up, you see, they put it over a flame, they heat it, and then they pour water into it. So they're going to pour a cup of water to see what happens. Well, having seen this up close with the Lausanne firefighters when I was a volunteer, it's a disaster. It's going to create a fireball. Technically, it's not an explosion, even though, loosely speaking, we can call it that. Why does it happen like that? If you take water and pour it into oil, or pour it into molten metal, or pour it into other heated chemicals, it always turns into a fireball. It always ends up erupting. And if you're close to it, well, it can cause huge burns. But why? Let me explain the principle to you. Water boils at roughly 100 degrees. When it boils, what happens? It increases in volume, it becomes water vapor. Its volume multiplies by about 1,600 to 1,700. So 1 liter of water suddenly turned into 1,700 liters of steam. This water vapor wants to escape, it wants to get out. So let me tell you, let's imagine that the oil here is over a flame, right? And then what happens is, for example, it's heated to 300 degrees. Typically, this happens sometimes. You have a housewife, she lets the oil boil, she leaves, and suddenly she remembers and comes back. Half an hour later, there's a pungent cloud in the kitchen, and she says to herself, "Oh, I messed up." So what is she going to do? Typically, people do this. They go to the window, they open it to air out the place. The moment she opens it, behind her, the oil catches fire. Why? Because you get a draft. So what's going to happen is that the oil is going to catch fire. Here, the risk, the right method, what is it? The right method is to stop the fire, to turn off the flame under the oil. And then, if it flares up, if it's on fire, just leave it as it is. If it catches fire, cover it with something. Even fire extinguishers on oil are dangerous because when you use extinguishers on, for example, burning gasoline or something like that, we did that at the fire station. You don't take it. No, I mean, just let me explain. You have a canister, for example, water or gasoline that caught fire. If you attack it with a fire extinguisher, you could end up in a flamethrower situation because with the pressure from the extinguisher, you can spray flammable liquid. So you have to be careful. In any case, generally what you need to do is cover the flame because oil, I don't have the exact formula in mind, I could tell you about it another time, but it consumes quite a bit of oxygen to burn. So you just need to smother it with a towel and that's enough. Even if it's not perfectly airtight, usually it won't keep burning. Now, what kind of accident has happened is that people took a cup of water or just water, took the pan, put it under running water and turned on the faucet here. So water, which is heavier than oil, what will it do? The water will come here. I'll draw it in red. So the water will come here, you see? It'll come here. Since it's heavier, it'll sink. With our current temperature, what will happen? It will, by the time you count, you don't even have time to count to 1, actually, it's very fast. What will happen is it will heat up, it will boil, turn into steam, and that steam will immediately escape very abruptly, completely just like that. As it escapes, what does it do? As it escapes, it carries the oil with it. It carries billions of droplets of oil with it. If you look at your pan here, I'm looking at my pan from above, you see? Well, if you look here, you only have this contact surface between the oil and the air. But when the oil is sprayed in the form of billions of droplets, well, you have a huge surface area between the oil and the air. And this time, you get a mega fireball. It burned quite a few people. So let's keep this pattern in mind because that's what's going to come into play that day. So we're going to go on May 30, 2024. We'll be in Tennessee in a factory that belongs to a company that's part of the HEF group. The HEF group is a French group that's present in many countries and has several sites in the United States. 15 people work at this site and they have to do what's called a nitriding process. Nitriding, Americans say nitridation, which might be a bit easier to pronounce, but what is it exactly? When you look at parts, sometimes airplane parts, engine parts, crankshafts, gears, all that, well, sometimes what they do is give them this treatment, which is a surface treatment. That means the part, once it's made, will be thoroughly cleaned and then immersed in several high-temperature baths containing chemicals. Several steps. So when it's done quickly, it can take a few hours. When done more slowly to go deeper, it can take several days. And then we can also repeat the cycle 2 or 3 times. For example, there are several ways to achieve this. It can be done using gas phase, plasma, or liquid methods. There are several ways to achieve it. Here, we're going to talk about the liquid method. What's the goal? The goal of this treatment is to strengthen the surface. The surface will become stronger, more resistant to wear, for example. There are several interesting characteristics, but one of them is greater resistance to wear. So for your information, and this is where you see the beauty of chemistry, the process was invented a little over a century ago, basically in the early 1900s. And it was much later that people tried to explain from a chemical standpoint how it works, because chemistry is fundamentally a very practical, very pragmatic science. It's not a science based on abstract theory. Very often the theory comes afterwards. It's a bit like airplanes flying. That's not chemistry, but airplanes flying. And much later, someone asked the question, but how is it that something heavier than air can fly? Yes, that's how it is. Very often things are advanced by technicians, not by scientists. Scientists always come late and try to explain how. But in any case, what I'm telling you is that I'm keeping it simple, but we're going to talk about just one step that interests us, because it's at this step that the disaster will occur. This step is what we call the oxidation step. You can imagine you have a bath, an oxidizing bath. And this bath contains 2 things. It contains a liquid made of molten salts. So it's not a saline solution. These are salts that have been heated until they become liquid. For example, you can take table salt, NaCl. If you heat it to 800 degrees, it will become liquid. It will be liquid salt. And sometimes we have practical reasons to do this. So here, what we're going to do here is mix NaOH in a tank. So NaOH, everyone knows it's caustic soda. It comes in the form of flakes and all that. Now, caustic soda is extremely dangerous to use. It's not toxic in the sense of, I would say, arsenic or sodium cyanide or anything like that. That's not the idea. But it's very, very, very irritating. It's very caustic, as its name suggests. It can cause terrible burns. When you mix that in water, when you take water and you add the flakes to it, always in that order. Never ever pour water onto the flakes. Always in that order. Mix gently. The water will heat up. And you can even make the water boil. You can dissolve, which is pretty amazing. You can dissolve, 3 kilos of NaOH in 1 liter of water. The ability of this salt to dissolve is absolutely extraordinary. So it gets very hot. It's very basic, so a very high pH. Be careful if anyone puts their hand in there. On the skin, it can cause terrible burns. It attacks more aggressively than acids, all else being equal. It attacks the skin, so it destroys the skin quite quickly. It also draws water out of the skin because, as I told you, it's very hydrophilic. It loves water. I'm telling you, it's really capable of absorbing water from tissues. And on top of that, it denatures proteins. You know that a drop of NaOH in the eye makes the eye turn white immediately. It's not like, we'll just put some water and all that. You can put water, of course, it's always recommended. But the vision is destroyed. So it's a very, very dangerous substance. So what we're going to add with it, in there we'll mix it with another salt, which is NaNO3. NO3. It's sodium nitrate. The NO3 group is the nitrate group. Every time you hear the word nitrate, look for it. There's NO3 in it. So nitrate, let me give you another example. For example, if I tell you NH4NO3, that's nitrate. Ammonium, that's here. This group here, that's ammonium. Nitrate, That's a fertilizer. It's a fertilizer. And this fertilizer has caused, I can tell you about it if you want, it has made widows and orphans. Why? Because when you look at what he's telling you, look at this nitrogen, you have N, you see you have two N's there, and those two N's are not in the same oxidation state. Where are they? They're in the same molecule. So just by looking at it, it tells you that it's not very stable. And there you go, but we'll talk about it another time. But it's a very good nitrogen donor, and plants really like nitrogen. That's why it's used as fertilizer. So all of this, we're going to heat to 400 degrees. So all of this, we're going to heat to 400 degrees. There you go, 430 degrees, I think, something like that. So it becomes liquid in this tank here. So it's boiling a bit like a witch's brew. So it boils like this, and the color is green. So the color is green. Why is it green? It's a bit surprising because these two, okay, are not green. They're white flakes. We mix them in water. It gives a clear white liquid. There's no reason that by mixing them we should get anything green. There's absolutely no reason. So probably here we have contamination with copper salts that must come from the products or parts we've put inside. So copper is very beautiful when you look at copper. What's extraordinary about it is that in copper chemistry, c'est que chaque fois qu'un sel, copper has something else. It has a different color, and it's very beautiful. I really like copper chemistry. So as I was saying, what's going to happen here is that the client had sent tubes. So these are long tubes like this, 2 meters, 2 meters, 3 each. He sent 6 of them, and he asked us to put them through this process. So what we did at first, we received them in April, so about 2 months before the tragedy. We took one, we put it through the whole process, we sent it to the client. The client said, yeah, that's great, do the others for me. So they received 6, and now they're working with 5. So these tubes have a characteristic that should have been a deal breaker. They should never have been processed in this factory. But you should know that the HEF group, as was explained after the investigation, had already had incidents before. They had at least 3 such incidents themselves. In addition, other competing companies have also had their share of incidents, even accidents, quite regularly, and sometimes with many victims. So it's a process that's very, very dangerous. What's the danger? It's that if you try to put an object with a cavity inside into the bath, so an object that's hollow inside, so the tubes were hollow inside, there was a cavity. There's a space, except that this space had 2 holes of 5 mm each, 2 holes on each side. And then with that, we said it's not a closed space, it's an open space. Since there are 2 holes of 5 mm, one might ask the question, does a 5 mm hole make the space open? You see, it's a question to consider, and you'll see here what it leads to. So what we're going to do is move our tubes from one bath to another. So to put them in the bath, what we have is a basket, like a deep fryer basket. We put the tubes inside, and we dip it vertically into the bath. So since the tubes are heavy, there are cranes up there. There's a remote controlled crane, and we have a technician who stands behind a kind of metal panel, a sort of shield with 2 windows, 2 plexiglass windows, and then he watches, and with a remote control, he will submerge the tubes, he will lower the basket. Up to that point, it's clear. So what they do is they run the whole process, and then once we're done with that, we put them in water to cool them down. They put them in the water, then take them out. And when they take them out of the water, there's a problem. They wait for an hour, they come back. When they touch one of the tubes, it's hot. It's burning hot. And then they realize something. They realize that there might be water inside. You see, they realize that's the problem. There might be water inside, or maybe some residue from that inside. They can't manage to empty it. Actually, what happened is that when we look at one of the 5 mm holes, when we took it out from here, we put it in the water bath. What happened is that that salt created a blockage. Because the salts, when they cool down, well, what they do is they harden. Right now they're liquid because they're at a high temperature, but once they cool down, they will harden. So what happened is that the salts created a blockage, so they closed up that hole. So given the situation, they were a bit stuck. They took a wire, they tried to open that hole to break that salt blockage, but they couldn't because probably behind it there was still more salt that had solidified. So they were really stuck. They didn't know how to continue. So what they did was they took the phone and called the process engineer, but they only had one process engineer for several factories. He wasn't on site and he was hard to reach because he only worked for the CEO. He only worked with the CEO of the company. So what they did was they got him on the phone. They explained, they said, we have a salt blockage. We're in a really tough spot. What do you want us to do? We can't get it out. It's as hard as concrete and all that. So what does he tell them? The process engineer tells them, in this case, the only way to melt this salt blockage is to put the tubes back in the basket and lower them back in there. You put them back in the bath. There you go for a few minutes, and you wait to see what happens as it heats up. And then the salt plug will come off. After that, you take it out again and let it drain well, okay? They will follow these instructions. So it's 9 o'clock in the morning, they're going to lower the tubes. Let's imagine that this is our tube. There you go, it's there. There are 5 that have been lowered. Here, I'm drawing just one for you. So actually what happens is that at first they thought there was mostly salt stuck inside. Actually, they have a salt plug. You see there was a salt plug at the bottom, and then there was also water that was trapped behind it as well. So there was water in there. So remember that. We're pretty much following the same logic here. So we have water trapped inside the tube. So when they put the tube with water, there was, I don't know, 2 or 3 liters of water inside. The temperature was 430 degrees. What did the water start to do? The water started to heat up. It immediately vaporized inside the tube. But since it couldn't go anywhere, what happened? It started to increase the pressure in the tube and leak a little bit from the top. Because we see the small 5 mm hole, it started to leak a little. Donc, the 5 mm hole is not able to allow the pressures to equalize. Because we have quite a lot of water, 430 degrees, a small 5 mm hole, that will never be enough for the pressure to equalize. It's too weak. So what happened is that our operator who is there, he's 45 years old, he's here, he's behind a screen. Well, what happened is that he sees that there's steam coming out. He's watching the mixture and suddenly he sees steam escaping. Normally at this point, what he should have done was run and run very fast. He thought, I'll take the tubes out. There's a problem. I'll take the tubes out. He presses a button to start the crane lifting the tubes. The tubes are just starting to lift when the head here is going to blow off under the water pressure. The head is going to blow off and water in the form of steam will get in there. You see, very violently. And what is it going to do? It's going to lift all the contents of this tank. That means 2 tons of NaOH and nano, 3 at 400 degrees are going to be blown into the sky. And when you look at the surveillance camera footage, which isn't very good, you suddenly see a kind of green cloud. And inside, there's this guy who's behind that little piece of sheet metal. Let's say we should have protected him. Actually, so here the solution is very hot. That one, yes, it's hot at 400 degrees, but this one is the worst. Because not only is it at 400 degrees, but it's caustic. This stuff can destroy your skin, even at room temperature. So at 400 degrees, I'll let you imagine. So what's going to happen is that here we have 2 tons of this product that will rise into the sky and fall back down here. And then the alarm goes off in the factory, everyone is running everywhere, and the firefighters arrive. So we're going to find this guy. He suffered 2nd and 3rd degree burns over 95% of his body. So the firefighters are going to take him, they'll bring him to the hospital where, not surprisingly, he will die the same day. When you look at the investigators' images, when you look at the metal sheet that was supposed to protect this guy, you can see that one of the plexiglass windows is missing. It actually melted. With the heat and the corrosion, literally, that window doesn't exist anymore. So the guy died. There was several injured damage, of course, extensive property damage, in the sense that the factory was closed for 8 months. So the factory didn't reopen until the following year, just so you know, 15 people were out of work and all that. So it was a big deal. And today, what the HEF group has put in place at the site has changed. When you look at how they work today, they've set up on all those tanks, because there are several tanks. And then with a crane, they move the parts from one to another. They've installed a kind of complete enclosure. It's basically a huge metal box. And actually, people are outside and then they work from the outside. So they still have little windows. I imagine they're reinforced. Maybe it would have been better to even remove those windows, seal them off completely, and put cameras and a big light inside. But in any case, today, this kind of incident wouldn't be possible, because even if we put water or something else and there was an eruption, it would stay contained inside this sarcophagus. That's it. Donc, aldosterone. I hope this is useful to those watching. If you're interested, I'll make more. Because personally, I really like China. I closely follow these stories about industrial accidents because there's a lot to learn, and aviation for me is just a type of industrial accident. And sometimes I even feel frustrated that I don't talk about other things, that I don't branch out beyond the channel's topic. But honestly, if it's something that's appreciated, I'm willing to talk about it from time to time. That's it. Thank you, my friends, for watching this video this far, and I'll see you in the next one. See you very soon.